In this video, we will be discussing about tests related to carbohydrates. But what's a carbohydrate? Just a basic classification I would like to present here so that we can understand the ideas shared in this video easily. Carbohydrate is either a monosaccharide or a molecule made up of monosaccharide. So that could be disaccharide, oligosaccharide, and polysaccharides. So monosaccharides are the building blocks of all these other carbohydrates, whether it's disaccharide or polysaccharide. What are monosaccharides? Monosaccharides are either aldoses or ketoses. So, what do I mean by aldose? Is like they will have a CHO group, an aldehyde group, and they will have multiple OH groups also, right? And by ketos, I mean that there is a ketone group and then there is a CH2OH group on the top of that. So generally the ketos have a ketone group at C2, carbon number 2. So there is a CH2OH group above that and then other carbon containing hydroxyl group, alcohol group below that. So these are aldoses and ketoses. Disaccharides are made up of monosaccharides, which could be aldose or ketose joined together. For example, the sucrose is a molecule which is made up of glucose and fructose. And then there are oligosaccharides, no common example, polysaccharides like starch or cellulose, which are made up of glucose units. So let's begin our discussion like how to identify these carbohydrates. So what are the tests which are used in laboratory to identify these carbohydrates? So the first one in the list is Molisch test. Okay. So this test is for pentoses and hexoses. So by oses I mean aldoses or ketoses, and pentoses could mean like a pentoaldose or a pentoketose also. So it could be either an aldose or a ketose with 5 carbons, and hexoses I mean it could be either aldose or ketose with 6 carbons. And this test could also be used for molecules which give pentoses or ketoses on hydrolysis. So if you understand this, then this means that practically all the carbohydrates which we have will give this test, because glucose, fructose, these are, let's say glucose. Glucose is a aldohexose. It has an aldehyde group and it has 6 carbons. Fructose is an ketohexose, so it will also give the test. Ribose, which is present in the DNA, and RNA to be more exact. In DNA we have 2-deoxy version of ribose. So ribose also is a aldopentose, so it will also give a test. Maltose is a disaccharide which is made up of glucose units, so it will also give the test. Galactose is a C4 epimer of glucose, so it will also give the test. Lactose is made up of galactose and glucose, so it will also give the test. Starch is made up of glucose units, of course alpha ones, so it will also give the test. And cellulose is made up of beta glucose units, so it will also give the test. So all the common carbohydrates which we know will give this Molisch test. So that's a good point to start with, Molisch test. What is the procedure for this test? So you have to mix this pentose or hexose sample with concentrated H2SO4 and then use the Molisch reagent, which is alpha naphthol. What is alpha naphthol and all these things we will discuss a little bit. Let's see. This is your hexose, right? It could be either aldoketose or aldohexose or ketohexose. So when you treat this with concentrated H2SO4, it's a dehydrating agent, so it will extract 3H2O out from the molecule, and the molecule will stop dehydrating when it reaches to this aromatic compound which is called furfural, but it's the 5-hydroxymethyl version of furfural here. So what is the mechanism behind that? You can try on your own. So it's simple dehydrating, but keep a look on aromaticity when the molecule is going to achieve aromaticity, so you can take like be cautious, and then you can, after removing 3H2O, you can reach to this molecule, which is 5-hydroxymethyl furfural. This is for hexoses. If you have pentose, then the dehydration will give furfural without the 5-hydroxymethyl group, just the furfural, right? So you can see it's an aromatic compound. The ring is aromatic with a CHO group here, and here also the ring is aromatic with an oxygen, and there is a CHO group here. Okay, so and then whether it's the hydroxymethyl furfural or the furfural, you can use the Molisch reagent, which is alpha naphthol. And what is a naphthol? So what is a naphthol? You know naphthalene, you know benzene, and then you know naphthalene, and then on benzene if you put an OH group, then that is phenol. So on naphthalene if you put an OH group, then you can call it a naphthol, and that could be done in I think two ways only. So here, or maybe you can connect the OH here, right? So this is the alpha one, this is the beta naphthol. Okay, so we have alpha naphthol here, and alpha naphthol can also go electrophilic aromatic substitution. It has this site which is activated for electrophilic aromatic substitution, and here we have a carbon with a delta plus, so it's like an electrophile, this carbon, and it can attack here, and you can do a normal electrophilic aromatic substitution. This X I have written here with the furfural because it could be either hydrogen or could be a methyl hydroxymethyl group. So anyways, this X is also here, and then this can get connected like this at the para position of OH group. And then once again you see here the alcohol group will pop out, and you can protonate and dehydrate it, and then once again another electrophilic aromatic substitution with the second beta naphthol will give you something like this, right? So you can see here is the furfural unit and two naphthol units joined together, and then there could be some oxidation, and it's the same kind of oxidation which happens with phenol, which gives benzoquinone, and that happens, and then you get a purple colored dye like this. So the procedure is interesting, and what you get finally is a purple colored dye. So that's how you identify most of the carbohydrates in laboratory, by Molisch reagent, by Molisch test. Okay, so then there is a variation of this test, variation of Molisch test, which is called rapid furfural test. Instead of the concentrated sulfuric acid, you will be using hydrochloric acid, and this will be used to differentiate glucose and fructose, because the fructose will dehydrate faster, and we are using a better acid also, I think, HCl, and the ketoses tend to dehydrate faster than aldoses. Why so? Why so? That's an interesting idea, that's an interesting question. If anyone can answer, I would like to see the answer in the comment. If anyone doesn't answer, then I will comment few days later what is the answer. So the ketoses, the fructose will dehydrate faster than glucose, and it will react faster, and in the rapid furfural test, fructose will be winning over the glucose, and it will react within 30 seconds. So this is rapid furfural test. And then we have another test which is Anthrone test, which is very much similar to these two tests above, and same as Molisch test. And what is an anthrone? First of all, so you know this is anthracene, right? And you have to think of a ketone, and you have to think of the idea of anthracene together. So you can think of this anthrone molecule. This is like the central ring doesn't look like aromatic here, but aromaticity is not a ring by ring kind of phenomenon. Anyways, but this is anthrone, and it can tautomerize to anthrol, which is the active form in the anthrone test, because here is the activated site for electrophilic aromatic substitution. In naphthol we had a similar kind of a molecule, but here we have anthrone, and this is the site where electrophilic aromatic substitution will occur, because we are going to use the dehydrating agent also in this test, just like the Molisch test. So dehydrate the sugar to furfural derivative, and then EAS with anthrol, and then you will get another dye which will be of some color. So this is also for practically all sugars, pentoses and hexoses to be more exact. Okay, Then there are some tests of carbohydrates which are based on whether the sugar or the carbohydrate is reducing or non-reducing. So what is a reducing sugar? Reducing sugar should have a free CHO group, an aldehyde group, because aldehyde groups can very easily get oxidized to carboxylic acid groups. So reducing sugars should have a free CHO group, or maybe by some simple reaction they can generate a free CHO group in themselves, in their molecule. For example, D-glucose, as you must know, in solution it exists as an equilibrium mixture of these three molecules: alpha D-glucopyranose, linear form, and the beta D-glucopyranose. And you can see that in the linear form it has a free CHO group. So 1% is enough, and the oxidizing agent will be used here, and this sugar will be the reducing agent. It's yeah, the sugar will get oxidized, so it will be the reducing agent, and there is a CHO group here which can get oxidized to carboxylic acid groups. So such sugars are called reducing sugars, which can produce which have a CHO group, a free CHO group, or can either generate the free CHO group. But the interesting thing is that the ketoses are also are also capable of generating a free CHO group by tautomerization. Let's take a look at this. This is the carbon number 1 and this is the carbon number 2 of a ketose. So it has a ketone group here and a primary alcohol group here. So the first tautomerization, I will take an H from here and I will shift it to here, and then I'll get an enol like this. And when I keep when I do the reverse, but this time I will use this hydrogen. I will use this hydrogen and I will shift it here, and then I will shift the double bonded O carbonyl group here, right? So this is an enol from both sides, because there is an OH here also, and there is an OH at this side also. So you can do the reverse in two ways. So in one of the ways you will get back to this ketose, and in the other way you will get an aldose. So when you get an aldose, so this carbon number 2 gets chiral, right? Because it now has H and an OH group and two other groups attached to it. So this could get chiral in both the configuration. So for example, the D-fructose, if you take a D-fructose, it can tautomerize to D-glucose and D-mannose. D-mannose is the C2 epimer of glucose. Okay, hence one can say that whether it's an aldose or a ketose, whatever monosaccharide we have, they will be reducing sugars because they can generate CHO, free CHO group in their molecule. What is an example of a non-reducing sugar? So the most common example is sucrose. Sucrose is the most important example of non-reducing sugar. It's a non-reducing sugar because both its rings are locked due to linkage between anomeric carbons. So when sucrose molecule is formed, both the anomeric carbons are connected, and both the anomeric carbon, you see, don't have a free OH group, so that they can tautomerize back to the aldehyde or the ketone group. Okay, so I'll tell you a simple idea. If you have to check whether a ring can open up or not, so suppose this is the oxygen in the ring, and you have to check these two positions. These two bonds can break up, and the aldehyde or ketone group can be generated here. So for that to happen, you need an OH at either this side or this side. You need an OH here or an OH here. If that's not there, then the ring can't open up, because this is how the ring closed at the first place. If you know how the ring was closed, then you can know how the ring will open up, because it's the reversible process. Okay, let's let me give a little bit more detail. So suppose this is a sugar molecule, and this is the OH which was used when the ring was closed. So this O with its lone pair attacks on this carbon, and this H shifts here, right? So when the ring gets closed, this C has an OH group. This is the anomeric carbon, and this C has an OH group, and it gets linked through an oxygen. So if this H is present here, then the reverse process can happen. If it's not there, then the reverse process can't happen. So while the formation of glycosidic linkage here, both the OH got used up and an ether linkage has been developed. So there is no OH on this carbon and on this carbon. And also you can check here also there is no OH, and also you can check like here also there is no OH, right? Just to be more safe. Okay, so now we understand which carbohydrate molecules can be reducing. Only those molecules which can generate a free CHO group. So when you are dealing with a disaccharide, you will have to think whether the ring can open up or not. Because if the ring can't open up, then there cannot be any free CHO group. Even if the ring open ups with a ketone group, then again by tautomerization you can reach to a free CHO group. Now let's see what are the tests for reducing sugar. The first one is Tollen's test. It's a ammonical silver nitrate. Tollen's reagent is basically ammonical silver nitrate. So you use AgNO3, which is soluble. It generates an Ag plus ion, and then ammonia is the complexing agent here, which stabilizes the Ag plus ion in the solution. And what happens that the Ag plus, which is in a complex form, will get reduced to Ag and give a silver precipitate, while the aldehyde group will get oxidized to this. So you can write a complete balanced equation also about for this, but that's not the purpose of the video. So I, the medium is basic and then you can balance this thing. But yes, Tollen's test can be used to check whether a sugar is reducing or not. Then we have a Fehling's test. In the Fehling's test, we have a Fehling A solution, which is a copper sulfate solution, which generates copper 2 plus ion. And then we have this potassium sodium tartarate. Okay, so potassium sodium tartarate contains these tartarate ions. So this is your tartaric acid, as you can see. It has a COOH group on both ends, and then two alcohol groups, two OH groups on the carbon in the middle. So there are four carbons here. Okay, tartaric acid is very interesting because it can exist in three forms, and it's one of the examples when we talk about chiral carbons, when a molecule have two chiral carbons. So at that time, one of the most real examples which can be given by anyone is of tartaric acid, which can exist in three forms, meso and two enantiomeric forms also. So this is your tartarate ion, and this tartarate ion is similar to the Tollen's reagent. You had a metal ion and then a complexing NH3 group, right? So here you have a metal ion Cu2 plus, and this is like a ligand. This is a bidentate ligand, so it will form a complex with Cu2 plus ion. But when the redox reaction will occur, the Cu2 plus will get converted into Cu plus, and which will form the oxide, the cuprous oxide of copper Cu2O, which is brick red precipitate, right? And at the same time, this oxidation will also occur. So in the Fehling's test, you will get a brick red precipitate which will indicate that the sugar is reducing. Then you have Benedict's test. It's exactly the same as Fehling's test, but we have citrate ion here only to complex the Cu2 plus. So what is citric acid? So this is citric acid. It's present in a lemon. The lemon, when you um, the juice from the lemon, when you extract the juice from the lemon, so in that juice you have citric acid, and this acid is also very interesting. It has three carboxylic acid groups, as you can see, and then in the middle, on the middle carbon, there is an OH group also, and then two CH2 methylene groups also. So you have overall 1 2 3 4 5, a chain of 5 carbons, and on the middle carbon there is a carboxylic acid group and a hydroxyl group. This is your citric acid, and if you remove these H plus from here, here and here, you get the tridentate ligand citrate ion, which will be complexing the Cu2 plus. But when the redox reaction will start to happen, the Cu2 plus will get converted into cuprous oxide, which is red in color. Very much same like that. Okay, wait a minute. Yeah, and then we have Barfoed test, which is again similar to the above two tests, and in this test you have Cu2 plus with acetate ion, and I hope everyone knows what an acetate ion is. It's If you have an acetic acid, you remove the H plus from here, you get an acetate ion, and this is a monodentate ligand. So this is in this you will have the Cu2 plus acetate complex, which will get reduced to cuprous oxide. Okay, so three tests here which are almost the same with Cu2 plus. So with Cu2 plus, and let's try to arrange them alphabetically. So which are the complexing agents we are using? Acetate ion, acetate, and then citrate, starts from a C, citrate, and then the third one is tartarate, tartarate, whatever. And let's try to alphabetically arrange the name of the tests. So the first one will be Barfoed. It's matching, Barfoed, and then citrate will match up with Benedict, and then the third one was Fehling, and it matches up with the tartarate one. So alphabetically they are in sequence, so that's how you can remember it. Barfoed comes first, then Benedict, then Fehling, and in the name of the complexing ions, acetate comes first, and then citrate, and then tartarate. Fine. But with the Barfoed test, there is a very interesting twist here. It's the twist is like the reaction turns out to be slower for reducing disaccharides. For disaccharides, which are reducing in nature, and they can also give this test, but they turn out to be very slow. So it makes it possible to distinguish between monosaccharide and disaccharide, and that's how the Barfoed test is used mostly in the laboratory, to distinguish between monosaccharide and disaccharides. Both of them could be reducing, both of them can give the test positive, but the disaccharide will be slower. What is the reason behind it? uh, mm, you can guess. Maybe, I think maybe it's a the acetate ion is a good enough ligand, is a better ligand than the other two ligands. There could be something here, but I have no idea because there is no explanation in the textbooks. So maybe if you have any idea, you can share it in the comment. Okay, so let's do a quick recap. How can you differentiate between glucose and fructose? Molisch test? No, because glucose and fructose both will give positive Molisch test, right? Both positive. Because Molisch test is practically for all carbohydrates. Rapid Furfural test, yes, this was the test which was used to distinguish glucose and fructose initially, but this is based on the speed of the reactions. It's based on the fact that fructose will dehydrate faster than glucose. And then Anthrone test, no, both will give a positive test result. Tollens, both will give a positive Tollens test. Fructose will also give a positive Tollens test, because people who are thinking that fructose is doesn't have any aldehyde group and it wouldn't give Tollens test, they are wrong, because it can tautomerize to give an aldehyde group, as discussed before in the video. So it's a reducing sugar also. So Fehling test also both positive, Benedict's test also both positive, Barfoed test also both positive. These four tests are based on reducing quality of sugar, right? And then someone can say that I don't like the rapid Furfural test because it's based on the speed. Mechanism is same and the test will happen for both of them, and it's only based on the speed. Is there anything else? So then there is again another test, which is Seliwanhoff's test. But the thing is that this is also based on speed. You see, the mechanism here is also the same. You are using an HCl in this test and you dehydrate a fructose. So I'm taking an example of fructose. Glucose can also get dehydrated into the same compound, but the dehydration of fructose will be faster. And this time in the Van Hoff's test, instead of beta naphthol, which was used in Molisch test, we are using resorcinol, and which is yeah. So this is the difference here in the Molisch test, and like the second reagent which is used to make a dye is different in these kind of tests. The first step, which is dehydration, is always the same. So resorcinol is been used here, and then you get a dye, and which will be of any color, but the fructose will react faster. Once again, this is based on speed. So Seliwanhoff test or rapid Furfural test, both of these tests which are being used to distinguish between glucose and fructose, is based on speed. Okay, so then you can say that I don't like the Seliwanhoff's test either. What to do? So the question which is which is arising here is, in the laboratory you wouldn't be asking this question because it's so easy to differentiate between a glucose and a fructose just by tasting them. Fructose is the sweetest sugar, right? So you can, if you're sure that one of the sample is fructose and the other one is glucose and both of them are edible, and you can taste the two samples, and just by tasting you can tell that which one is fructose, because fructose is the sweetest of all sugars. Thank you.